Events of the past and present shape tomorrow. Our vital concern is you, today's youth, for our future depends on you. Before attempting to figure out where we're all going, it is imperative for us to have a strong awareness of where we have been. To untangle today's problems, we need to understand yesterday. This film series hopefully will in part make you aware of people, places, and events which have helped shape our nation and our world. Manufacturers Hanover is pleased to sponsor this educational film. Manufacturers Hanover, it's banking the way you want it to be.
In less than a century, aircraft have developed into machines essential to commerce, travel, and international relations. Today, aviation science continues to race ahead. Recent advances include new aerodynamic designs, fuel-efficient high-performance engines, and innovative helicopter technology. This is a report on new high-technology aviation. The essence of aviation progress is often radical new designs in aircraft. This is a prototype of one such aircraft design named Starship One. Such a configuration with small forward wings and large ones far back is called a Canard. Instead of a central vertical fin, tip sails at the ends of the wings serve as rudders to control sideways movements. The small forward wings control pitch. The tilt of the nose provides additional lift and stabilizes flight. The forward wings are adjustable, straight out in slow flight, swept back at high speeds to minimize drag. New, lighter, stronger materials, titanium and plastic reinforced with graphite fibers, improve performance. The turbine-driven propeller engines conserve fuel while allowing a cruising speed of over 400 miles per hour. Another innovative Canard which utilizes advanced materials technology is the Avtec 400. This non-metal aircraft can fly 6 people coast to coast non-stop at 400 miles per hour, getting 10 miles per gallon. The outer shell material is about 16 times stronger than conventional construction materials. One component takes the form of a honeycomb sandwich. The resulting sections, stronger pound for pound than solid steel, are bonded together. Unlike the skin fastened over frame designs of conventional aircraft, the Avtec involves more than 50 pre-molded sections glued together, saving weight, labor, and assembly time. The new all-composite aircraft has no metal structural components at all. Once the designers set the values for strength, stiffness, and other properties, composites were blended to make materials that met those specifications. Because of these materials, the plane weighs only about 5,000 pounds, a third less than similar conventional designs. The key feature, the Canard wing, allows lift to be controlled from the nose. The composites improve the plane's aerodynamics. Lacking rivets and seams, its smoother airflow increases both speed and fuel economy. This Canard, the X-29, was built to demonstrate various kinds of advanced technology. Its swept forward wing, for example, is designed to reduce air drag and increase maneuverability at speeds close to the speed of sound. The wing is of lightweight epoxy composite material, providing stiffness and strength. It is aero-elastically tailored, constructed of layered strips of various thicknesses and orientations, so as to resist several flight stresses. Its curve can be controlled in flight to take the best shape at different speeds and altitudes, and do the jobs of both up and down and sideways flaps. The X-29 has an electronic control system. The pilot uses computers both to monitor aircraft performance and adjust engine and airfoils. The X-29, a new tool to perfect a variety of technologies, extending the possibilities of flight. A second focus of aviation research is lowering fuel costs. One answer is a new generation of fuel-efficient jet engines. The basic fan jet design is unchanged. Air is drawn through an inlet fan mixed with fuel, ignited, and the combustion gas provides thrust and spins a turbine, which drives a gearbox that spins the inlet fan. The new technology includes a higher performance turbine, newly designed gearbox, and stronger discs and blades that reach higher speeds. An electronic engine control precisely manages fuel delivery, turbine speed, and other variables. Throughout development, more improvements were added. Changes in blade twist and attachment angle, as well as geometry and clearance. The hot section or combustor was given special attention. Studies of combustion gas flow were done using tinted fluid. The final design sets up an even temperature gradient with no hot spots. Engine reliability tests were carried out next, including heating, cooling, and even lightning strike conditions. Flight tests followed, the engine placed in a special carrier and flown on the wing of an ordinary aircraft. In the end, engines must satisfy both aircraft builders and government regulators. The final certification tests include ingestion of rain, ice, and debris. After 5 years of development, the new fuel-efficient engine is ready for full-scale flight tests and the needs of the next decade of air travel. Since its invention, the helicopter has undergone major changes and improvements. The newest advances include a main rotor blade of graphite, titanium, and fiberglass, giving longer life and greater lift. While this rotor head design replaces ball bearings with rubber and steel laminates, such elastomeric bearings work without either oil or sliding parts. New kinds of testing facilities include wind tunnels for combining rotor with airframe, whirl stands for evaluating front and tail rotors, and hub and shaft test stands to measure stress limits. Today's helicopters include a large number of switches, dials, and other controls, making piloting very demanding. In tomorrow's cockpit, many controls will be replaced by computer-operated electro-optical displays, TV screens that present flight data in compact visual form. Now in flight test, This advancing blade helicopter allows speeds of up to 300 knots and can hover as well. Its two counter-rotating rigid main rotors, one above the other on a common shaft, permit the advancing sides of both rotor discs to generate lift. This rotor research aircraft with rotors, wings, and auxiliary jets is used to test new flight concepts. It can fly like a helicopter or as a fixed-wing aircraft with wings, jets, and rotors. It also has the only helicopter crew escape system in the world. The blades are released in sequence, then rockets lift the crew out. The XV-15 twin-engine tilt rotor is another major innovation. Advanced weight-reducing technologies which make it possible include powerful new engines, composite materials, and computerized controls. The tilt rotor is capable of both ground and mid-air conversions between forwards, backwards, sideways, and hover modes of flight. A single switch controls the swiveling of the propellers. Its 25-foot diameter prop rotors allow 350-knot cruising speeds and cruise altitudes of 25,000 feet. In cruise flight, performance resembles that of a turboprop plane, the wings providing high lift and the rotors forward thrust. Potential uses include search and rescue, offshore oil platform support, transportation between city centers, and business-related tasks. Using helicopter mode for landing both reduces noise pollution and allows steep approaches. Designs now exist for 3- and 4-engine tilt rotors, carrying up to 100 people. Today's new aircraft incorporate advances in many disciplines: aerodynamics, structures and materials, propulsion, and controls. One expert has called them computers that fly. Continued research is expected to lead to major new improvements in the decades to come.
Manufacturers Hanover has been pleased to sponsor this educational film. Manufacturers Hanover, it's banking the way you want it to be.